Through pipes, exactly. So you can build a full application using pipes, and in many cases you will actually see on top of the shell you will see some GUI, which is basically an extension to the shell, giving a graphical representation to some of the standard shell ways to do things. Yeah. Okay. So, when you're through this, you will have explained most of what a modern operating system is, and given time, you could give small examples of files and how you use files, of shells and shells. And your 10 or 15 minutes will have passed. Okay. Anything else to say? Next one, name at least 3 different IPC methods. Well, IPC is inter-process communication. So you have to pick at least 3 and shortly describe how they offer and what their use, how you use them, the applicability of those IPC. So, one, two, three. What should I write on the first one?
Shared memory.
Shared memory? Which is a rather complex one. But it's true, it's a way for processes of communicating. We could go through each of those when we have a number to talk about. What else? Semaphores.
Pipes.
Pipes. So now we have 3. How many more could we take after that?
How about files?
How about files? Isn't that the easiest way to communicate between processes? Put your data on a USB stick, put it in your pocket and take it to another computer and put it in that computer. Now you have another process over there communicating with the first one using files. So files is a very useful communication. It can be used to real-time communication, more or less real-time communication, or it can be used to communication with a lot of delay, represented by putting the file on the USB stick and carrying it to another system. So files are a very convenient way of communicating between processes. We have used that for many years. Anything else we should mention?
Sockets.
Sockets. Quite good example as well. Yes?
Message queues.
Message queues. Yes.
Signals.
Signals. I would mention that as well, because this is the lowest level of communicating. It's just sending a signal from one process to another, indicating that a certain event has happened. There's not much information in that communication, except that the event you're looking for has happened. Decide what you're going to do about it. So it's the lowest, so to say, the lowest order of communicating. Yeah. We could go through most of these so that at the examination you can freely pick whatever you we could also, when we're talking about files, we could take mapped files as well, because mapping files are also a convenient way of communicating. Yeah. So, what is shared memory? How is it possible to share memory? Because normally we say processes have isolated address spaces. They cannot access data in the memory of another process. No process can access data in the memory of another process. So how on earth can they share data? How is it possible?
You map a bunch of virtual memory to a file that is with the other process.
Yeah, so basically we have to say each process has its own virtual memory, and no process can access the virtual memory of another process. This process, the memory of this process maps into physical memory using a page table. And this process has, in the same way, a page table mapping the pages of this process into virtual memory. So if we decide that this part of my virtual memory is going to be shared with another process, that process could say, okay, I want to have this piece of memory representing the memory which I share with another process. Then we can ask the kernel to map these two virtual memory areas in the two different processes into the same physical pages in memory, which suddenly mean that whenever you access a piece of data in this part of virtual memory, it will actually be a piece of data in this physical memory, which is also accessible through this part of the virtual memory. So now these two virtual memory areas in the two processes contain the same data, namely those data which are mapped into this physical memory. Which means when you are accessing data, updating data in this process, you have to make sure that it doesn't conflict with what's going on in this process. They contend for the same area in physical memory. So we have to use signal and weight or whatever to indicate when we are updating data which are shared with another process. So that's basically what is done. So this getting shared memory involves that we have to call the kernel in order to ask the kernel to map the same virtual pages into the same physical area. So it will enter the same pages. If these are pages 2, 3, 4, those pages 2, 3, 4, and 2, 3, 4 will be part of both page tables pointing to the same physical areas. Why would we do that? It sounds a bit complicated. What's the benefit?
It's fast.
It's faster, because now you can access all those data as if they are part of your. Now you can communicate with another process just accessing memory in your own memory space. Then the other process will see the result of those changes at once. So it's a very fast way to communicate, and still all other parts of memory are protected from one another. So it's only that part of virtual memory which you deliberately want to be shared, which is actually shared. All the rest is still protected. So it's a fast, efficient way to communicate. Yes? What about semaphores? What are they?
They can control access to.
Yes, that's a function, yeah. What is a semaphore?
It's a number.
Sorry?
It has an indicator number. That's easier.
Yeah, that's true. When you program it, you get access to the semaphore through a semaphore ID, which is like any other file is a number identifying the resource. We sometimes call it a primitive, which means that it's a basic operation. It couldn't be divided. The signal cannot be divided. It's a basic operation which cannot be divided. You can also say that it's an atomic operation. Why do we need atomic operations?
So to